Hello everyone, and welcome to this video on rationalizing a denominator containing one term. Alright, so in this video I'm going to go over several examples where we have an expression that has a denominator with a radical, right? A square root, a cube root, a fourth root, etc. And our goal is to, rationalize this denominator, meaning I'm going to rewrite it as an equivalent expression without a radical in the denominator, so that we have a rational number in the denominator, thus the term rationalize. So I'll write that out again. Right. So the instruction for all the examples today is to rationalize each denominator. And I said it out loud a second ago, but what this means is I'm going to write an equivalent number, write an equivalent expression, pardon me, with a rational number. Basically, no radical. In the denominator. That's what we're talking about. And we're going to do this through a clever multiplication by 1, where I'm going to multiply the numerator and denominator of my fractions by the same number. Right, that way it's like I'm multiplying by 1. And here's how it's going to work. So we'll have a fraction, with some numerator. Let's say a in the numerator. I don't really worry so much about what's in the numerator. And we're going to have an nth root in the denominator, say the nth root of b, in the denominator. And again, this whole video is going to have a one-term expression, right? A denominator with one term only. And then what we're going to do now is I'm going to multiply the numerator and denominator by the same expression, the same number, another nth root. I'm going to do it so that the radicand in the denominator becomes a perfect nth power. So this is b to the first. I would like the exponent to be a multiple of n, right, to be considered a perfect nth power. Well, if I take b to the first and multiply by b to the n minus 1, remember when you multiply two expressions with the same base, you would add the exponents. 1 plus n minus 1 would just be n. And I'd get the b to the nth power. And I do the same thing in the numerator as well. And we end up with, a times, the nth root of b to the n minus 1 power divided by, and then we have, the nth root of b to the nth, right? We have the nth root of a perfect nth power, and that's what we're going to try to get. All right, we're going to try to get a perfect nth power in the radicand of the denominator radical. And then once it is a perfect nth power, we can simplify it. All right. So this would be whatever a is times the nth root of b to the n minus 1 power in the numerator. And then that denominator would just simply be b, or the absolute value of b, right? Depends on whether or not n is even or odd. Okay, so if n is even, remember this is technically going to be the absolute value of b. If n is odd, it'll be just b itself. So again, this denominator depends on if n is even or odd. Sorry about the tininess of that on the bottom of the page. All right, but that's the goal. All right, I'm trying to get the radicand in the denominator to be a perfect nth power, and it depends on what the value of n is. What is the index of the radical? Okay, so my example here, the first one, and all the examples are like this. We've got 1 divided by the square root of 3. So you see this is a denominator that is not rational, right? The square root of 3 is actually an irrational number. So we're asked to rationalize this. So what I like to do is first factor the radicand, if it's just a single term like this, completely. Right? Which, 3, the radicand of that radical, 3 is already factored completely. It's already prime. It's 3 to the first power. And then we're going to multiply, using that product property, multiply to get a perfect nth power in the radicand. Right, so I want exponents that are multiples of 2 here, right? This is a square root, so I'm looking for perfect squares in the radicand. So perfect nth power. And then, of course, simplify at the end. Right. So I'm starting here with 1 divided by the square root of, and when I factor 3 completely, it's just 3, 3 to the first power. We're going to multiply the denominator again and the numerator. We're going to, you can't just multiply the denominator of a number by something and not the numerator, right? You have to multiply both the numerator and denominator by the same number so that it's like you're multiplying by 1 and not actually changing the value of the expression. So this is a square root. I'm going to multiply by another square root. All right, so that way I can use the product property and actually put these together, square root with square root. And here I have 3 to the first. I have 1 factor of 3. If I want the exponent to be a multiple of 2, I just need to add 1 more, right? It's 3 to the first. I just need 1 more to get 3 to the second. So inside this square root, I'm just going to put 1 more factor of 3, another 3 to the first. And if I multiply the denominator by the square root of 3, right, we must also multiply the numerator by the square root of 3 again, so that way it's like you're multiplying the original number by 1, right? Anything divided by itself is 1. Okay, and then we multiply the numerators. 1 times anything is itself, so 1 times the square root of 3 is the square root of 3 in the numerator, divided by, and again, make this bar long enough so I know that it's not in the square root, right? It's outside the square root, not part of the radicand. And then the square root of 3 times the square root of 3, I can use that product property as the square root of 3 times 3, or the square root of 9, or the square root of 3 squared if you want to write 3 squared, 3 to the second, right? It's a perfect square now. And we can simplify that, right? So the numerator, that radical is already simplified. There's no perfect square other than 1 that goes into 3 evenly. So the numerator is the square root of 3 divided by, again, big long bar here. The denominator, when simplified, the square root of 9 is simply 3. And now this expression here has a denominator that they would say is rationalized, right? The original, the square root of 3 in the denominator, that's not a rational number. Square root of 3 is irrational. But this one, the number 3 in the denominator, 3 is a rational number, right? It's 3 over 1. It's a ratio of 2 integers, a rational number. Okay, and notice again, no more radical symbol, right? No radical in the denominator is what we're looking for here. Great, so that was one example. And of course, you know me, I like to check, is the number I started with, that expression, does that have the same value as the number I ended with? All right, so radicals, irrational numbers, I'll punch this into a calculator. So the first expression I started with was 1 divided by the square root of 3. And it's giving me this 0.57735026992 da 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 da. Look at the expression at the very end. It is the square root of 3 in the numerator, and then after that divided by 3 in the denominator, and great, it is indeed the same as the number I started with, so we did a good job. It's 0.57735 something. Wonderful. All right, I'm going to keep checking that. Is my expression at the end actually equal to the expression I started with? Because that should be the case. Great. All right, the next example, I'm doing the same thing. I'm asked to rationalize the denominator, and there's only one term in the denominator, just this square root of 8. All right, so I have the square root of 5 divided by, and then the denominator is the square root of 8, and 8 is not a perfect square. So what I have in the denominator is an irrational number. Remember, the square root of a non-negative number that's not a perfect square is irrational. So I'm asked to rationalize. So like I said before, the first thing I want to do, all right, the numerator is the square root of 5. That can't simplify. All right. I'm not really worried about the numerator right now. Right? Again, we're asked to rationalize the denominator. So there's the square root of 5 in the numerator. And then the square root of 8. I'm going to factor 8 completely. 8, right, is actually 2 to the third power. 2 times 2 times 2. When you break it down completely to a product of primes. All right. So this is the same thing as equals square root of 5 in the numerator, and then this square root of 8, all I did was rewrite 8 as 2 to the third power. So you can see that this is not a perfect square also here, because the base of 2 has a power that's not a multiple of 2, right? If it was a perfect square, the power would be a multiple of 2. Alright, so now comes I'm going to multiply the numerator and denominator by the same thing, right? And they're both, these are all square roots here, so I'm going to multiply the numerator and denominator by a square root, and I'm going to have the radicand of this root be such that when it's multiplied by the radicand of this root, we get a perfect square, right? Something with a power that's even, a power that's a multiple of 2. Well, right now it's 2 to the third, 3 factors of 2. Well, what's the next multiple of 2 after 3? It's 4. So in order to ensure that I got a perfect square in the radicand down here, I just need one more factor of 2. So I'm going to multiply by the square root of 2 to the first, right? I'll write to the first here, but just the square root of 2. Same thing up here, multiply by the square root of 2. Okay, so look at what happens. The numerator, square root of 5 times the square root of 2. Those are both square roots of non-negative numbers, both real. I can use that product property, put those together. That's the square root of 5 times 2, or 10. All right, 10 for the radicand. And big bar here, separate the numerator from denominator, divided by, and the square root of 2 cubed times the square root of 2 to the first would be the square root of 2 to the fourth. Remember, this is a perfect square. And you could, if you want, because I'm dealing with square roots here, write this as a square. Alright, so the numerator I still have, the square root of 10. The denominator, I have the square root. And then think about how 2 to the fourth could be written as a square, something with the second power. And that's going to be using that power to a power rule, power to a power property. 2 to the fourth is the same as 2 to the second squared, right? 2 to the second. Remember that power to a power rule, I would multiply those and that would give me 2 to the fourth. And then we can simplify, right? We can take the square root of a square, of a perfect square easily. So the numerator, square root of 10, that's as simple as that gets, right? There are no perfect squares other than one that go into 10 evenly. So the numerator is simply the square root of 10 divided by, right, big bar, then the square root of 2 squared, right? The square root and the square are basically like undoing each other, and then I get, technically the absolute value of 2 squared, but that's just 2 squared, positive 4. Right, this is the 2 squared would be left over. 2 squared is 4. And there you go. Here is a number, a fraction, where the denominator is, rational, right? It's rationalized. Okay. And let's double check, is the square root of 5 divided by the square root of 8 actually equal to this square root of 10 divided by the square root of 4, divided by 4, sorry. So let's check. So let's do the original number, the square root of 5 divided by the square root of 8. All right, I'm getting 0.79056941 blah 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 blah. And let's take this last number that we said it was equal to, and hopefully it is, right? It better be the square root of 10 in the numerator, and then after that divided by 4 in the denominator, and look, it is indeed the same number, 0.79056941, so on. Great. So that worked out. Now, looking at this same example, we could have done this another way as well. All right, so I'll put this over here. If you'd like, and I'm only going to do this for this second example, you could simplify the radicals first and then rationalize, and then simplify again. So the square root of 5 divided by the square root of 8, the square root of 5, that radical, that can't be simplified. There's no perfect square other than one that goes into 5. So that'll stay the square root of 5 in the numerator. Then the square root of 8, there is a perfect square that goes into 8, and that would be 4. So the square root of 8, right, you could break up to the square root of 4, which is 2 squared, times 2, and there's a perfect square, something squared, 2 squared, times a non-perfect square, and then using that product property, we have this again, the square root of 5 in the numerator divided by, and then this will break apart to the square root of 4 times the square root of 2, and the square root of 4 is 2, right? The non-negative, that's what the symbol asks for, the non-negative square root of 4, positive 2 times the square root of 2. All right, so I simplify the radicals first, and then I can rationalize. Where you see, this is not rational yet, right? In the denominator, I still have this radical. I still have the square root of 2 down here. But that's the square root of 2 to the first. And remember, I want to make the radicand a perfect square if I'm taking square roots. So this time I would have to just simply multiply the numerator and denominator by the square root of 2. Right? That would give me 2 squared, right? That would give me the square root of 2 squared, the square root of 4, the square root of a perfect square down here. And I multiply the numerator by the square root of 2 as well. And that would leave me with, the numerator, square root of 5 times square root of 2 is the square root of 10, divided by, and then down here I'd have, I have this factor of 2 that's not in a square root, so 2 times, and then the square root of 2 times the square root of 2 is the square root of 4. And so I have the square root of 10 divided by, and then this is 2 times 2, right? 2 times the square root of 4, and 2 times 2 is 4. So the square root of 10 in the numerator divided by, and then 4 in the denominator. And you see I get exactly the same number I got earlier, right? The square root of 10 divided by 4. But this time I simplified the radicals first and then rationalized. But doesn't matter which way you do it. Notice I end up with the same result anyway. So you decide which way you like better. Do you want to simplify more near the end and rationalize first, or do you want to simplify some radicals first and then rationalize? It doesn't matter really what order you do that in. All right. So my next example actually has a variable in it, right? So when there are variables in expressions, letters in expressions, I like to, if I remember to, I like to state the domain, right? What am I allowed to plug in for the variable? So this says, 5 in the numerator divided by, then in the denominator we have the square root of 10 times x. So I've got this variable x down there. I would like to know, what am I allowed to plug in for x in this expression? So that's the domain of the expression, right? What am I allowed to plug in for the variables? All right, so down here I have a square root, an even root, and I've done plenty of videos now on radicals, and hopefully you've been watching. When you have an even root, the radicand can't be negative. Well, 10's not negative, so that's okay. So this x can't be negative. So x can't be negative. Not only can it not be negative, it can't be 0 either. Right? Because if x were 0, you'd have 10 times 0, you'd have the square root of 0, which is 0. You'd have 5 divided by 0. Remember, division by 0 is bad. It's undefined. It has no meaning. So x can't be negative, and on top of that, x can't be 0. So the only values I can plug in for x are positive values. So x has to be greater than 0, or I could write this in words, x, the value I plug in for x has to be a positive number. All right, and let's just keep that in mind as I work through this, and then when I check at the end, is this expression truly equal to the expression I get in the end? Just know that I can only plug in positive numbers and test those. All right, so as I've been doing, the way I like to do things when I'm asked to rationalize a denominator with a single term, right? Again, there's just this one term down here. There's no addition or subtraction. We'll get into that in the next video. So I got numerator of 5, right? Not really worried about the numerator right now. I'm going to factor the denominator completely. So the radicand, right? So the square root of, and then 10 times x, when you factor it completely, would factor to 2 to the first times 5 to the first times x to the first, right? Okay, so then comes the rationalization part, right? This is a square root, so I'm looking to make perfect squares. I want the exponents on these to be multiples of 2. Well, that's again pretty easily done here. I'm going to multiply, the numerator and denominator by another square root, right? These are square roots. I have 2 to the first, so I have one factor. I just need one more 2. That'll make 2 squared, a perfect square. Then times, and then I have 5 to the first, so I just need one more 5. And that'll make 5 squared, a perfect square. And I have x to the first, I just need another x. Right, so times again, times x. That'll make x squared, right, another perfect square. Something with a power that's a multiple of 2 is a perfect square. And then the same thing in the top, to the square root of 2 times 5 times x. Now 2 times 5 times x is again just 10x. All right. So in the numerator, I have this factor of 5 and then the square root of 10x, 2 times 5 times x. This is not in a square root, right, the 5, so I can't put it inside here. You can't put these together. I can't use that product property, so it's simply 5 times the square root of 10x in the numerator. All right, divided by, and then in the denominator, when I multiply, now these are both in square roots, and as long as x is positive, right, we're saying that the only values allowed for x are positive ones. So we're going to assume here that x is a positive number, and as long as x is a positive number, these are both real, going to be reals, right, square roots of positives. So I can use the product property, right, if these are both real. And I'd have, the square root of 2 squared times 5 squared times x squared. All right, so my numerator, still has 5, factor of 5 times the square root of 10x. And the denominator, when you split this up, the square root of 2 squared is 2 times the square root of 5 squared is 5, and the square root of x squared. Now hopefully you remember this from before, previous video. When you take an even root of a perfect power, like the square root of a perfect square, remember this symbol, when you see this symbol with an even root, an even index, the result must be the non-negative root. They're asking you for a non-negative number. So usually we would do this, write x and then put absolute value symbols around it, right? Undo the square and then put absolute value symbols around it to ensure that the result is non-negative. So I could write that. I could say the times the square root of x squared is the absolute value of x, but remember the domain here. X is always a positive number. We are only plugging in positive numbers. So if x is positive, well then you can just say this is simply x, right? You don't need to have absolute value symbols around a positive number. So because x is positive, the square root of x squared is just x. And now look, my denominator is rationalized, right? There's no more radical. But it's not completely a simplified fraction yet. All right, remember, to simplify a fraction, I would like to have the common factors of the numerator and denominator divide out and become 1, cancel out, right? There's a factor of 5 in the numerator and a factor of 5 in this product in the denominator. So the factors of 5 divide out, and there I'm done. Those are the only factors that the numerator and denominator have in common. And don't cancel the x's, right? This is technically the square root of x, right? It's under a square root. This is not under a square root, so those are not the same factor. Same thing with the 2 and the 10. This is the square root of 10, not just 10. So 2 doesn't go into the 10, right? Because it's not, it's not in a square root. One's in a root, one's not. Those don't get canceled either. Please be careful with that. So the numerator, this is the square root of 10x divided by, and the denominator has factors of 2 times x left over. And there, that's as simple as it's getting. When after we've rationalized the denominator doesn't have a radical anymore. All right, and let me test this again. All right, I like to test my expressions with variables. I'll do it on the calculator, right? Is the number that I get in the original expression the same as the number I get when I have the final expression? Because if these are truly equal, if I'm saying this is equal to this, that means they should be equal for every value of the domain, right? No matter what I plug in for x, as long as I plug in a positive number for x, this will be equal to this. All right, so let me pick a positive number. And again, you can do this with all sorts of positive numbers. Just take whatever you want. I'm just going to plug in, 3 for x, right? So the first expression was, I have 5 in the numerator divided by, and then the square root of 10 times, and like I said, I'm going to have x be 3 this time. And let's see what we get. So that's 0.9128709292 blah 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 blah. Now let's go to the expression we said it was equal to and plug in 3 for x there. So the numerator of this expression is the square root of 10 times 3, 10x, right, inside that square root. Then divided by, and then again, if it has multiple factors, right, there's 2 times x down here, multiple factors. I put that in parentheses. Right, just so I'm dividing by that whole thing. And then in parentheses, the denominator is 2 times x, but again, I'm letting x be 3. Close parentheses. And look, oh, they are the same number. Wonderful, right? 0.91287 and so on. And try it out with other ones, right? This doesn't prove anything. It's just to, get me to believe that these are indeed equal as long as x is positive. So try plugging in, 5, 10, a million, 1/3, 1/5, 2/3, 7/9, 11/15, whatever you want. Any positive number, pi, square root of 3. You know, plug in any positive number for x, and the value of this expression should be equal to the value of this one. Great. All right, now those examples so far, all the examples so far have had a square root, a single square root in the denominator, one term. My next examples have higher roots, right? So here's one. I'm asked again to rationalize the denominator, meaning rewrite it as an equivalent number so that there's no cube root in the denominator. All right, so now that I'm taking a cube root here, right, we're going to try to make it so that there's a perfect cube in the radicand. Now, perfect cubes have exponents or powers that are multiples of 3, right? So I'm looking to make powers that are like to the 3rd power, the 6th power, the 9th power, 12th, etc. All right, well, I'll start off with, I'm going to leave it, numerator's 4. The denominator, right, you have the cube root, and I'm going to factor the radicand completely. Well, 3 is already factored. It's prime, right? So 3 to the 1st, right? I'll write the 1 here if you want. That's the cube root of 3 to the 1st. And then comes the rationalizing part, the multiplying the numerator and denominator by the same number. So these are cube roots now, right? So I'm going to multiply the numerator and denominator by some cube root. And I want to do it so that the radicand in the denominator is a perfect cube, has a power that's a multiple of 3. Well, 3 to the 1st I already have, so I just need 2 more, right, to make 3 to the 3rd. So if I have 3 to the 1st in this radicand, I'm going to multiply by the cube root of 3 to the 2nd, or 3 squared. That'll give me 3 to the 3rd, right, a perfect cube in the radical of the denominator. And that's just 9, or if you want to write 9 or 3 squared, same thing. And then I'm multiplying the numerator also by the cube root of 3 squared, right, or the cube root of 9. All right, now in doing so, we have the following. The numerators, multiply those. You got a factor of 4 times this cube root. This is not in a cube root, so I can't put these together. I'll just simply write those factors. 4 times the cube root of 3 squared, but again 3 squares is 9. So the numerator is 4 times the cube root of 9. And big division symbol, right, divided by. And then the cube root of 3 times the cube root of 3 squared. You can put those together with the product property, right? They're both cube roots. That's the cube root of 3 to the 3rd, right? It's the cube root of a perfect cube, the cube root of 27, right? 3 to the 3rd is 27. And now we can simplify our radicals. The cube root of 9, there's no perfect cube other than one that goes into 9 evenly, so that's simplified. So we have 4 times the cube root of 9 in the numerator, divided by, and then the cube root of something cubed, right, that just undoes each other, it's just 3. The cube root of 27 is 3. And here we go. Here's our fraction with a rationalized denominator, right? A denominator without a radical symbol like the original one had. And there aren't any factors in the numerator and denominator in common, right? So that is totally simplified. All right, and then as I like to do, all right, let's double check this. All right, the original expression was 4 divided by, and the cube root of 3. All right, and that's the number 2.77344597 da 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 da. The expression I said it was equal to this number here. And the numerator again has multiple factors, so I'm going to put it all in parentheses, just a habit of mine. Right? I like to have it all, my whole numerator in parentheses, my whole denominator in parentheses, especially if there's multiple factors or multiple terms. So in parentheses, I'm going to put 4 times, then we have the cube root of 9. Close parentheses. There's the numerator. divided by, and then the denominator has just this single factor, just the number 3, right? And look, hey, it's the same number again. Wonderful. 2.773445.097 and so on. So this worked out. But again, I was looking for perfect cubes this time, right? Not perfect squares. You got to pay attention to the index of the radical, the number and the little crook there. Okay. My next example. The same instruction, right? We're asked to rationalize the denominator, right? So I have the cube root of 3/20ths, which, if you use that quotient property for radicals, which I've had a video on using the quotient property to simplify radical expressions. You can look that up. But when you take a radical of a fraction, you can separate it. Do the radical of the numerator. So the cube root of 3 in the numerator divided by, and again make it long enough so you know it's not inside the radical, and then the cube root of 20 in the denominator. Okay? And then this is pretty similar to my last example, right, with the cube roots. Alright, so we're asked to rationalize this, rewrite it so that there's no more cube root in the denominator, no more radical in the denominator. Alright, so as before, I like to do this, we'll do keep the numerator the way it is. I'm not really concerned with the numerator just yet. So the cube root of 3, and then in the denominator the cube root of, and then I'm going to factor 20 completely. Now 20 is 4 times 5, and 4 is 2 squared, 2 times 2, and those are all primes. So 20, when you factor it completely, is 2 squared times 5, right? That's the same as 20. So I got the cube root of 20 in the denominator. All right, and now comes the part where I'm going to multiply the numerator and denominator by the same number. So it's like I'm multiplying by 1. And do it so that we have perfect cubes in the radicand of the denominator. So these are all cube roots here. So I'm going to multiply the numerator by a cube root, the denominator by a cube root. Okay. Now what's going to be in the radicand of this? Oh, look, there's 2 squared. I'm looking to make perfect cubes, right? Powers that are multiples of 3. So if I have 2 squared now, I just need one more 2. Right? I need 2 to the first. I'll just write 2. Right? That'll make 2 cubed when I multiply those, a perfect cube. And then the 5, the factor of 5, I only have one of those. So if I only have one of these here, I need 2 more to make a perfect cube, right? To make 5 cubed. So in the radicand of this, I'm going to put times 5 squared. Right? That'll give me 5 cubed. So I do the same to the numerator. Right? Multiply by the cube root of 2 times 5 squared. And 2 times 5 squared, that would be 50. Right? So this is the cube root of 50. 2 times 25. Right? You do the 5 squared first. Remember, you do exponents first before multiplication. All right. Now let's get to it. Now the numerators. Now these are both cube roots. So I can use that product property. That's the cube root of 2 times 3 times 5 squared. Well, I already said 2 times 5 squared is 50. Times 3 would be 150 for the radicand of the numerator. That's 3 times 50. All right, so the numerator is the cube root of 150, and that wouldn't simplify, right? The factors are 2 to the first, 3 to the first, and 5 squared. None of those have powers 3 or higher, so you can't pull out a perfect cube from that. So the cube root of 150 is as simple as the numerator gets. In the denominator, I'd have the cube root of, you have your perfect cubes. You'd have your 2 cubed times your 5 cubed. Alright, so numerator, cube root of 150 divided by, and then the cube root of 2 cubed would be 2. The cube root of 5 cubed would be 5. You'd have basically 2 times 5 down here, or 10. Right? You'd have 2 times 5 left over when you take the cube roots. And there we go. Right. The numerator and denominator do not have a common factor, and the denominator is, rationalized, right? It's rewritten without a radical. Wonderful. Now let's check. Is the original number equal to the number I got at the end? So the first one was the cube root of, and then inside that radical, 3 over 20, right? 3/20ths. So that's 0.5313292846, and so on. Now let's take a look at this last number, what we said it was equal to, and hopefully it is, right? The numerator has the cube root, square root, sorry, cube root of 150 in the numerator, and then after that, outside that, divided by 10 in the denominator, and oh look, it is indeed the same number again. Fantastic, right? 0.5313, so on. Great. Alright, I have just one final example here. We've had square roots with a single term in the denominator, a single term with a cube root in the denominator, like this one. I'm just going to bump it up one more notch, and you can keep going, do fifth root examples, sixth root, but I'm going to do one last example here where there's a fourth root, right? A radical with an index of 4 in the denominator. This also has a variable, so I will also be talking about, like I do in most expressions, that have a variable or variables in it. I'd like to discuss or think about what can I plug in, what's allowed to be plugged into that for that variable so that I have a real number output. All right, so before I get into the whole rationalizing, let's talk about the domain of this expression. All right, this is 3 in the numerator divided by the fourth root of p. All right, the variable's p here. Well, hopefully it's obvious that p can't be 0, right? Because if p were 0, you'd be dividing by 0. You'd have 3 divided by 0. The fourth root of 0 is 0. Any root of 0 is 0. So p can't be 0. Additionally, this is an even root, right? Square root, fourth root, sixth root. This is an even root. So if I want a real number output, the radicand, the number inside, can't be negative. So p can't be 0, and it can't be negative because of this even root. So the only numbers I can actually plug in for p are positive numbers, right? And this is kind of like an example I had earlier in the video. So p has to be greater than 0, right? Or I'll write that in words as well. P has to be replaced by a positive number, right? It has to be a positive number, something that's not negative and not 0. All right, great. Now that I've got that out of the way, well, let's do this. And this is equal to, again, numerator's 3. Not really concerned about that yet. Divided by, and then I've got the fourth root of p. P, that's as factored as that's getting. It's p to the first. So then, already got it. I already have the radicand of the denominator factored. Now, I just want to, comes the part where I multiply the numerator and denominator by the same number, the same expression. There'll be fourth roots, right? These are all fourth roots here. And the fourth root of what? Right? What's the radicand in these? Well, I'm taking the fourth root. So, what I want inside the radicand is to be a perfect fourth power. I would like the exponent to be a multiple of 4, right? So to the 4th, to the 8th, to the 12th, 16th, etc. Well, I've already got p to the first in there, right? That's p to the 1. So I just need 3 more to make p to the 4th, right? To make a perfect fourth power. So I would, have the radicand of this radical here be p to the 3rd, right? That will make p to the 4th when I multiply these and give me a perfect fourth power in the radicand. Same thing up here. Right, multiply the top and bottom by the same. So I have the fourth root of p cubed that I'm multiplying by. Okay. In doing so, right, the numerator is just simply, this is not inside a fourth root, so these don't go together. You just simply write these factors next to each other. I have 3 times the fourth root of p cubed. And that's it. And that's as simple as that's getting. Divided by, and then the fourth root of, p times p cubed. And again, and we said earlier, p is going to be got to be a positive number. So these will both be fourth roots of positive numbers, and those will be real. And since they're real, we can use the product property and put them together. And I'd have the fourth root of p to the fourth. Now again, just like with the square root one a couple of examples ago, normally when you take the fourth root of something to the fourth power, say x to the fourth root of a perfect fourth power, you'd have the absolute value of x, right? Again, when you see this symbol, the radical symbol with an even number index, square root, fourth root, sixth root, that symbol means, give me the non-negative root, right? So don't just write x, right? It's the absolute value of x. Same thing for this. The fourth root of p to the fourth would technically be the absolute value of p. But we already said earlier, p has got to be positive anyway, so there's no need to write absolute value of p, right? So if the number inside is already positive, well, then you don't need the absolute values, right? So that's what's happening here. P is positive, so that denominator is just, you can just write p. You don't need the absolute value of p, even though normally you would put it. And then the numerator is again this 3 times the fourth root of p cubed. And there we go. And there's the numerator and denominator don't have any common factors, and the denominator is rationalized, right? Doesn't have a radical anymore. All right, and then let's test it out. Now, I'm just going to pick one number. You can do it for all sorts of numbers, right? Pick any positive number for p and plug it in here, and then plug them in here in this expression. And what you get for this expression's value should be exactly the same as this one if I did everything correctly. Right? If these truly are equal, they should be equal for every value of the domain, right? Every positive value of p. Okay, so let me pick a positive number. How about 17, right? Just whatever you want. 1, 17, 1,000,000, 500,000, 278, a third, pi, square root of 3, whatever you want. But for any positive number, this expression should have the same value as this one. Well, let's check it out. All right, so if I'm gonna replace p with 17, all right, a positive number. Now the original expression is 3 in the numerator divided by, and the fourth root, right? So a radical with an index of 4 of p. And again, I'm letting p be 17. So when I let p be 17, the value of this first expression is 1.477437182. All right, and this other expression. Now my numerator has multiple factors, and you've heard me say, when something has multiple factors or multiple terms, and I want to make sure that I recognize that that's all in the numerator, so I like to put parentheses around it. So parentheses, I got the factor of 3 times, and then the fourth root of p cubed. But p, remember, I'm letting p be 17 here, so 17 to the third power. And there you go, right? That's close the parentheses. That's the numerator when p is 17. And then all of that divided by the denominator of p is also, I'm replacing p with 17. And I'm hoping I'm getting this 1.477 number back, and I am. Look at that. All right. And again, try it out with anything in the domain, any positive number for p, and that should happen. Right, the value of the original expression should be equal to the value of your final expression, right, if you're doing everything correctly. So I would test that out with some numbers if I were you. Always check your work. All right, great. All right, so these examples were all, you had one term in the denominator with a radical. In the next video, we're going to take a look at, what if there are what if there's more than one term in the denominator with a radical? What do we do then? And it'll be just with square roots, because the more terms you have, the more complicated it'll get. So we're just going to look at, in the next video, rationalizing denominators with two terms and only square roots in the denominator. Okay. And as I like to say at the end of these, try the best you can to learn the material on your own before you go out looking for help. As I find that when people take the time and the effort to learn something on their own, they tend to remember it better and for a longer period of time, and are more proud of themselves for it. So read the material, of course, read through the author's examples, perhaps even try to work out the solutions to some of the author's examples before you read how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously, do tons of exercises, practice problems, check the solutions to those if they're ever made available, so you can check yourself and track your progress, see how you're doing. And don't just give up on an exercise or a problem after one attempt or two little attempts. Don't give up so easily. Very often in mathematics there are several ways, several approaches that'll work for any particular problem. So if after several attempts and approaches at a problem you're still not getting how to do it, perhaps you should read the material again, maybe even a third time, more slowly, more deliberately, take good notes. And if you've been working on some problems, there's a good chance you have a better idea as to what the author is asking of you, what the author wants from you. So then when you read through again, or a third time, you'll have a better idea as to what to look for in the reading. You might, catch some things that you didn't catch the first time through, make working on the problems that much easier. But if after all that, several read-throughs of the material and several attempts at problems, you're still not getting it, still not making sense, well then, it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. There's tons of those too, like this one, or other videos that are better than this one. I assure you they're out there and they're easy to find. But just keep at it. Don't give up. Stay persistent. Keep practicing. And above all, try to have a positive attitude. You'd be amazed at the difference a change in attitude can make toward the learning of a subject. Believe in yourself, even through your struggles and failures. It's at those times when you're at your lowest, when you're struggling, when you're failing, that you can learn the most from your mistakes. That's when you learn, is when you make mistakes. So, stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it eventually. And thank you very much for watching.